Thanks, Dean. I'm very excited to be here, actually. I've worked on experiments and experimentation for over 10 years now. But weirdly, this is actually my first time at Code, despite having many collaborators and students who've come here. So thank you to the organizers for inviting me. It's a real pleasure, and it's been amazing to be here so far. So I'm actually just going to share, Sid said something yesterday on the panel, and I told him that I paused when he said it, which is it's nice to look out and see so many young people. And he and I are pretty much the same age, and I realized that made me an old person. And so because I'm an old person, I have the right to give a retrospective. So this is basically a retrospective on about 5 years of work on congestion and interference. So start with what's congestion. Congestion, broadly speaking, I'm an operations researcher by training, and so congestion, broadly speaking, is competition for scarce or capacity-constrained resources. Okay? So I've worked a lot in collaboration with marketplaces on experiments, and so this is a great example of inventory constraints being an example of a congested resource. You have limited inventory. Guests come to book that inventory, so of course if a guest books something, then that's not available for another guest to book. But I actually want to start with a different congestion story, which is one from Netflix. Sort of in a weird alter ego of mine, I've spent over a decade working with Netflix's adaptive streaming team on the adaptive streaming algorithm they use in their player. And when COVID hit, so this is from March 2020, they along with actually several other video providers, they implemented a cap voluntarily on their bit rates. Basically, it meant we're not going to serve the highest bit rate video, and the idea was to preserve network capacity by doing so. So at that time, obviously, we're all stuck at home, and there was overload on networks because of the resulting increase in streaming video. So what we did is, with Netflix, we ran an A/B test in a congested network to try to understand the impact. And there was a weird thing that happened, which is the A here was control, no bitrate capping, and B was treatment, which is bitrate capping. And the bitrate cap traffic actually experienced far worse network performance. Of course, the video should have been worse, but the network performance should not have been worse. You're sending fewer bits. Now, the reason this happened is that the treatment traffic was sending less as it should have been, but the control traffic compensated by grabbing far more capacity. And you might expect it to be actually neutral, right? That maybe just control fills in what treatment gave up. But it actually was worse than that. The interaction between them led to the naive A/B test telling us that treatment was actually worse for the network, which is odd, because that was not the goal. And that's interference, OK? That's interference. So today's talk is basically about how congestion leads to stronger interference in A/B tests. Why does it happen? I kind of gave you a little hint of that. When does it matter, and what should we do about it? So I'm going to start with some preliminaries. And because it's a 25-minute plenary, I'm deliberately staying away from a very detailed technical model. My student, Anushka, I think Anushka's right there. She'll be giving a talk later in the afternoon in the session on interference that'll have a little bit more of a precise technical presentation than I'm giving here. Broadly speaking, in the sequence of work that we've done on this topic, we've thought about modeling congestion structurally. And I just want to mention that as an aside. There's a lot of different ways that we can think about complex phenomena like interference, whether it's in networks or from a congestion, because of congestion. And I think in causal inference, we like to take a very non-parametric view of these problems. But the problem with interference is that inherently it's involving very complex interactions between units. And when you think about something like congestion, this is actually a type of interference for which operations researchers have invested a lot of effort in building structural models that are informative. And so for us, we built on that sort of background, which involved creating a stochastic dynamic queuing model of interference and using that to try to understand some of the properties of interference. So again, no technical details, just to tell you that's kind of what's going on under the hood. Okay? Now, I don't need to tell this audience what an A/B test is, but this slide is only here to just clarify exactly what I'm going to be talking about. I'm going to assume we're looking at a Bernoulli randomized A/B test. If you were thinking about a marketplace, for example, you could randomize on either side of the market, just for the purposes of what I'm telling you. I'm going to focus on randomization on the customer side. Essentially, you have some treatment and control groups with different fractions. The way I want you to think about treatment is that it's changing the likelihood that customers will book inventory. Okay? And that's kind of sort of why I want you to focus on the customer randomized test. Now, what do we do when we run one of these tests? The first thing you should be doing is not actually thinking about estimation. You should be thinking about your estimand. So what are you trying to estimate when you run a test? And it's important to understand that in the presence of any type of interference, this is actually an important detail. Typically, what we're looking for, the first estimand that you would think to write down is the difference between global treatment, everybody being exposed to treatment, and global control, all right? Everybody being exposed to control. So this is exactly the estimand we're going to be interested in here. Throughout the talk, I'll use green to denote treatment. I'll use blue to denote control, okay? Now, estimation. So for the talk, I think this is another interesting aspect of working on interference generally. A lot of these things I didn't appreciate when I first started working on these problems. But there's really two different ways you could start to think about interference. One is you could ask yourself, what do I do about interference? And I think really honestly, because of an accident of history, took a very different approach, which was to ask, what if you just do the naive thing that you would do in the absence of interference, then what happens, okay? And this is kind of the naive thing that you would do in the absence of interference. You would just form a difference in means estimator, and you would form some kind of simple naive variance estimator. This, of course, leaves out regression controls or any of the other fancy stuff that we might do, just as a simple starting point, right? Maybe I just look at my data, look at the treatment group, look at the control group, form a difference in means estimate, and then form the associated variance estimator, and maybe look at a t-test statistic. So that variance estimator, that'll be more important downstream in the talk. For now, you can just focus on the fact that we use the difference in means. Notice that sort of looking at the world this way is clearly completely ignoring any correlation structure in the booking outcomes. And that, of course, is where the interference is coming from, all right? Okay. Okay, so now let's briefly recap what is the impact of congestion. So I kind of qualitatively told you there is such a thing as interference that's arising because of congestion. Just to really drive that point home, let's look at it in a very, very simplistic example where I have 4 customers arriving here and they're randomized to treatment and control. Interference fundamentally just arises because if a treatment customer arrives and books a listing, then they take that listing off the market. And because that listing is now off the market, when the control customer arrives, the state of the system has been impacted by what the treatment customer did. That's interference. Interference statistically is that the outcomes, the potential outcomes of one unit depend on the treatment assignment of another unit. So this is exactly how it happens here. And the only reason I'm kind of presenting it this pedantically is I kind of want to show you why the non-parametric view of congestion is hard from a potential outcomes perspective. Because what you would need to write down is the network of interactions between all customers and all subsequent arriving customers. That's really just not the right way to look at the problem. And this is one of the meta points here is that I think this type of problem motivates looking structurally at the nature of congestion. Now, because that sort of interaction is happening over time, you could see that that's going to impact the control customer's booking behavior. Now, what feature of the system is going to drive that impact? Look at one extreme where there's essentially an infinite number of listings available. And it's clear that it almost doesn't matter that the treatment customer books something. And that's what I like to call the Netflix example, not the one I gave you, but just if you're a viewer on Netflix and you watch a movie tonight, that has no impact on what movies I can watch. So Netflix, at the user level, does not suffer from any congestion interference. The movie inventory is essentially infinite, okay? That was not true when they used to ship out DVDs, but I just dated myself like Sid did yesterday. On the other hand, right, if you're looking in a very supply-constrained network, or something where the demand is very high in its arrival relative to the supply, then it's very clear that this interference effect is going to be non-negligible, okay? So that was an important result in this paper with Hannah Lee. I think Hannah's sitting over there, yeah. And Inessa Leskovich and Gabriel Weintraub, that the more supply-constrained the market is, the more congestion there is, the larger the bias is. This paper actually has another important insight, which is that because the congestion is stronger, when the constraint is tighter, you actually want to randomize on the shorter side of the market if you want to minimize interference. And that's actually quite counterintuitive, because if you look at a market where you have a large amount of demand and a small amount of supply, the temptation is to always randomize on the demand side, because it looks like that's where I have the most samples. Sort of qualitatively, the thing is that your interference is going to be driven by the fact that the congestion constraint's very tight on the supply side in that case. So you actually want to randomize on the shorter side of the market. A recent thing that we've been working on is, one pushback I get on that is, but my variance will be lower if I randomize on the long side of the market. And the issue with that is, I hope you can see that in an extreme where you have 10 million customers and one listing, your variance is not smaller because you randomized on the 10 million customers. All right? So you don't actually save on variance by randomizing on the long side, and you definitely lose a lot on the bias. So that's like one major lesson of that paper with Hannah, is you really want to randomize on the short side of the market. Okay? So congestion leads to interference. So this economic phenomenon or queuing phenomena of congestion leads to statistical interference, which leads to bias in our estimator. Okay, now what to do? This has occupied a large fraction of my life in the last 5 years. This is a long list and not exhaustive of things people have tried to do on this. Just this problem, congestion, not even network interference, just interference related to congestion. And the stars are things that I myself have participated in or worked on in different papers. I have a reference slide at the end of the talk that you're welcome to take a look at. But that's not really the point of my talk today. Having worked on this for so long, one of the things that emerged, is the bottom line is like many of these are really hard to implement, okay? And they don't get done as often as they should. It's really fun to write papers on them, but you guys all, a large fraction of this room works on these kinds of experiments in the world, and you know that it's hard to get complicated experimental designs and or estimators off the ground. And so that led us to step back for a second and just ask, wait a second, like, do you have to debias? Okay? That seems like it's an obvious question for this room. Of course we have to debias. And here's a reason why maybe there's a little bit of a question mark there. So let's talk about decision making instead of estimation. Now, what does decision making look like? Decision making is like, do I launch this thing? And again, I'm being naive in this talk. I'm not doing anything very sophisticated, and I've already set up the difference in means estimator and the variance estimator for you. So decision making with those two simple things would be like take the t-test, right, the t-test statistic, and reject the null if that statistic is large. Okay? That's what that's the first thing that anybody does with their experimentation dashboard. Okay. So what is the goal of hypothesis test-driven launch decision making? There's really two goals, and again, these are the two goals you learn in Stats 101. One goal is you don't want to launch bad ideas, and the other goal is you want to launch good ideas, right? So formally, the first goal is you want a low false positive probability. You do not want to launch things that really aren't moving the needle. And the second goal is you want to launch things that do work. That's high statistical power. Okay? And so a crucial kind of technical point here is, if I write those two goals down, those goals are not the same as unbiased estimation. And therefore, it's not immediately obvious whether or not interference is affecting decision making in the same way it's affecting my bias. Right? So we talked through, like, qualitatively at least, what's the impact of interference on bias? How is it affecting decisions? It's a hard question in general. And so what we did in the paper, now this is another paper with Hannah and then with Anushka Murthy and Gabriel Weintraub as well. So what we did is we looked at a specific class of treatments that we call sign-consistent treatments. There's a lot of words on this slide, but let me just summarize it in a qualitative way. A sign-consistent treatment is something where the sign of the change in a customer's behavior doesn't depend on the level of inventory in the marketplace. Okay? Now, first of all, I just want to say that when we analyze experiments in marketplaces or in congested systems, we kind of implicitly make this assumption often anyway, because we just look at overall point estimates of what's happening, which essentially is saying that I don't feel like the state is really necessarily an important driver of the differences in behavior. But even if you put that aside, there's a lot of examples that really fall in this class. So things like increasing the amount of information that's shown to a customer. So these are some examples from different platforms. New payment flows, like mobile payment services that you might set up. These are things that both add friction, but then maybe also are changing customer behavior in a positive way. So you're not sure what the sign is, but qualitatively, you wouldn't expect that this sign is dependent on the amount of inventory in the marketplace. And then changes to the user interface, things like notifications. Okay? Now here's the key thing. If treatments are sign consistent in that way, meaning, again, that the change in customers' behavior, whatever that sign is, doesn't depend on the level of inventory in the marketplace, it's not just that bias doesn't hurt you. It's actually that it helps you. It actually helps you. And we found that to be a little bit of a striking result. So in particular, formally what we show is that the false positive probability is correctly controlled, and the statistical power is much higher than any unbiased approach. All right, so there's one way to think about this is there's kind of 4 results that lead to that. You need to show that when you look at the difference in means estimator and the naive variance estimator, they're doing the right thing when the null is true. And you also need to show that somehow that test statistic is getting bigger when the null is false. Right? So there's kind of numerator, denominator, and null and alternative. And so there's kind of 4 conditions. Anushka will talk a little more about that this afternoon. The most interesting technical result in here is the fact that the false positive probability is correctly controlled. That was extremely surprising. Anushka gave a short talk on that at last year's code. So I'm not going to focus on that. Those who know me know I would be happy to talk your head off about the technical details of that result offline. But I want to kind of just give you a little window into what's going on under the hood from a sort of more conceptual perspective. The key point here is that because this result kind of holds for these sign-consistent treatments, you're actually strictly better off not debiasing. Interference is letting you detect the effect better than you would have if you had tried to take the bias away. Okay? Because that's the case, it's sort of an odd situation where, on one hand, I'm working on a lot of papers that are helping people debias treatment effects. And on the other hand, in some situations at least, like I can conclude maybe that wasn't, that effort isn't worth it, right? Now, why does this kind of result arise? I think qualitatively, at least for a practitioner, maybe the most important thing to know is not the technical details of the false positive probability result, but rather why your power is higher. Because I think that's kind of the core driver of what's going on from a practical standpoint. And the reason your power is higher is basically because you overestimate the magnitude of the treatment effect. Okay, now why does that happen? So, just one thing I forgot to say. We're going to look at a case where, where the treatment makes listings more attractive to customers. So in other words, remember, sign consistency is regardless of the state of the market, a customer's sign in their behavior is the same. In this case, that sign is positive. The treatment makes customers more likely to book in any state of the market. Okay. So why do you overestimate the magnitude of the treatment effect? It's actually a very simple intuition. This is the experimental system, and I have a mix of treatment and control customers in this system. Okay? Now, when I go to global treatment, I've colored in everything green. And what does that mean? Blue customers are less likely to book than green customers, regardless of the state of the market. And therefore, when I move to an all-green market, I've created a more competitive market from a buyer's perspective. And if it's a more competitive market, the truth, which is the all-green, is going to look lower than whatever is going on in the experiment. So the experiment will overestimate the truth for the treatment group. And similarly, for the control group, the other way. You will underestimate the control group. Okay? And if you put these two together, then you overestimate the global treatment effect. Now, that's not the whole story. Right? The t statistic is difference in means estimator divided by square root of the variance estimator. We have to argue that the variance estimator is somehow not better when you use unbiased estimation. Those of you that have worked on debiasing know that there's almost always a bias-variance trade-off. When you try to take bias away, your variance almost always goes up. So intuitively, at least, it should not be surprising that the variance is also going to blow out. And so your numerator is smaller, your variance is higher, so your power is actually better doing this, like not trying to debias anything, than it is if you actually tried to remove the bias. Okay? All right, so what? So what? So like I have the fortunate accident of life that I'm an academic and I can write papers like this and that's great, but that can't possibly be the whole story. And it's not. It's definitely not. So really I think the lesson for me of this work is not like don't ever debias. The lesson is that whether or not you choose to debias has got to have something to do with what decision you're going to make. It cannot be made in a vacuum. Okay? So I'm going to tell you at least 2 examples where, yeah, you do need to debias. And that's not where, like what I told you, the bets are off. Now, the first one is just, OK, I told you that I'm proving this result in a situation where the treatment is sign consistent. If it's not consistent, meaning sign inconsistent, and what's a good example of a sign inconsistent treatment? Think about something where a platform that sets prices, like a ride-sharing platform, chooses to lower prices when inventory is high and raise prices when inventory is low. Now, this is a case where the customer's behavior will change depending on the state of the market, the amount of inventory in the market, right? Because I'm either raising or lowering prices relative to control. And basically, in a nutshell, what we show is that as soon as you open up the class of treatments to be as big as sign inconsistent, really anything, all bets are off. You can have things go wrong in either direction. Your false positive probability can be way off from your nominal control of, let's say, 5%, and your power can be far lower than what you get by debiasing. Okay? Now, I think to make this question interesting, you really want to refine, like, in what ways are you sign inconsistent? But that just goes back to the point, which is, well, why does that matter? Because of whatever decision I would make downstream. Okay? Now, the other kind of big issue is sort of that the metrics I care about might impact the decision making. I focused on a particular metric, which is the booking rate. Okay? But if I'm trading off, let's say, that metric against a cost of deployment, now it's clear that the treatment effect matters, right? Because I need to know whether or not actually the lift is sufficient relative to some deployment cost. Another key example is, let's say, not just that I care about bookings, but I actually care about profit, or I care about revenue. And in another piece of work that we've done recently, this is with another graduate student, Ori Page, and also with Gabriel. You'll notice a running theme here. Gabriel and I have spent a lot of time working on these questions together. One of the things that we showed is that when you run pricing tests, then it's possible that you actually get a flip of the sign systematically. Not just because of stochastic variation, not because of variance, but just systematically, the bias can be so bad that it actually flips the sign on your estimate. Again, this is for profit and not for bookings, all right, or revenue. The most recent thing we did here, we just submitted this paper, and the last exercise we did in this paper was an empirical exercise, which showed that this is actually the kind of thing that, especially for listing randomized experiments, there's reason to believe that it's a not uncommon phenomenon. Right? So I think this is kind of a situation where, yeah, debiasing actually matters. OK, so returning to Netflix, we didn't believe what we saw. And one of the things we did in that particular case, what's a good example of debiasing, one thing that's commonly used is a switchback experiment. So we ran a switchback. And indeed, what the switchback showed is these metrics that were negative actually kind of performed the way they should perform when we ran the switchback. Right? So this is in a paper from a networking conference. So I have about 3 minutes left, and I want to zoom out a little bit and just sort of provide a little bit of perspective both on this work and kind of what motivates me these days. So I think in some sense, like I said this already, but I just want to drive the point home. I'm able to hold the ability to work on debiasing and think about the situations where debiasing is not important at the same time. And the reason is just because my vision is downstream of the estimation problem. Like, my vision is on the decision problem. Okay? I think there's something else going on here that's important, though, which is, besides the life that I have as an academic, I've also been lucky enough to spend a lot of time talking to and working with practitioners in industry on experiments. And there's just a systematic thing that I see, which is that data science and industry, I have a colleague at Stanford that referred to it sort of as the site ops of decision making. Now, what did they mean? They meant, we're really called in for reliability, for validation, for understanding. And the picture I have in mind here is like, other people make the decisions. And then they call on you for inference. And what is inference? Inference is understanding and validation. And ultimately, what you have developed as understanding and validation feeds back up into that decision pipeline, right? And I hope I'm seeing some nods in the room. I think you can relate to this kind of experience of what it means to be data scientists in an environment where the decision making is an envelope around you. But I think kind of the world we're in is one where it cannot look like that. It cannot look like that. So for a variety of different reasons, one of which is just that AI is massively accelerating the rate at which just possible decisions get generated. Right? And it's also changing the nature of understanding from inference to the next decision. And so kind of where I think you all are moving and should be moving is to a world where the data scientist's role is not just at the orange layer. The role is actually full circle in the loop from decision to inference and back again. All right? So I had a lot of fun earlier. This is like last fall, and the paper came out earlier this year with Yav and Dave Holtz and Martin and former student Sven Schmidt, working on a paper that was kind of broadly about building experimentation capability beyond the basics. And I think one of the themes in that paper is this idea of kind of a self-learning organization, but also the central role of a data scientist in enabling this kind of picture. So I think one of the main takeaways that I have from this kind of work is, at least when I teach students in my classes or when I'm supervising students, to push towards thinking about decision making as driving your inferential goals. I think it'll just make you a better business leader besides just being a good data scientist. So let me stop there. Thank you.
Thanks a lot. That was great. Actually, just since you've already left the stage, I think we'll just go to the next talk, and we'll take some more questions later. So our next plenary speaker is Hongseok Namkoong from Columbia University. Take it away.
Thanks, Dean. Gosh, Ramesh is a tough act to follow. For those of you who don't know me, my name is Hong. I'm an ML researcher at Columbia. I work at the interface between AI and operations research, decision making, as Ramesh was talking about. And one of the topics I'm most excited about these days is that of self-improving agents. LLMs being cognizant of what they don't know and being able to write their own post-training environments, right, to optimize their goal on some downstream business task. This is awfully AGI-pilled, right? And what I believe is sort of the central intellectual bottleneck in order to get to this self-improving loop is the ability to perform adaptive experimentation, which is obviously a hallmark topic, right, in this community. So that's sort of what I'm going to talk about, different insights that we can use to scale up adaptive experimentation capabilities. Now, a bit more grounded way to, I guess, motivate what I'm about to talk about is not, AGI, but rather thinking about concrete agentic systems, right, and getting them to perform long horizon tasks. So here I have a plot where on the x-axis we have the date at which these LLMs are released, and on the y-axis on a log scale, we have the length of time it takes for humans to complete the task. And you see that it's actually quite remarkable how about every 7 months, right, the length of the tasks that these agents can perform, it's doubling. And this is what's leading, right, people like Johari, the CEO of Anthropic, to claim that he's going to replace half of all entry-level jobs in a couple of years. I obviously don't hold that view. And what I view as sort of the central intellectual bottleneck, again, is that these LLMs, they don't know what they don't know, right? And as a result, they are not really capable of making new discoveries. So these LLMs, they contain all of humanity's digitizable knowledge, but they haven't really made any new discovery of note in the last 5 years. And if you compare them to MBA students that I teach, right, they know nothing. Their prior is extremely diffuse. But you throw them out in the real world, and in 5 years, they become hyper-competent workers. Well, some of them, right? And this is sort of what I view as intelligence, not how much your brain contains right now, but your ability to actually sharpen your posterior and decide which additional information to put into your brain. And of course, a more technical way to talk about this is to think of this as the ability to quantify your own level of uncertainty. There's been many classical works, right, that study this topic. There's lots of really interesting ideas, right, in these multiple literatures. But by and large, they haven't really been incorporated into GPT-4 or 5, right, to the extent that I can think about. And the reason is that despite all the incredible things we've seen in AI over the past 10 years, in some sense, we still only know how to do two things as a community. One is to come up with a fictitious differentiable loss that you can optimize the heck out of on internet scale data using SGD. And to do this, to scale up to internet scale data, you got to come up with a whole lot of interesting ideas, right? New architectures, new optimization methods, and so on. And to weed out good ideas, right, from bad ones, you got to do empirical benchmarking. You got to validate your ideas on some held out data set. And any framework that doesn't really neatly fall under these two pillars, right, they quote unquote don't scale, right? There's many operational bottlenecks to actually scaling this to GPT-4 level. And mostly this is sort of the bitter lesson, right? To quote Rich Sutton, the more of the human intelligence, right, the more of your discovery that you are trying to build into the learning pipeline, the less scalable it's going to be. So to sort of really drive this point home, right, in the context of uncertainty quantification, let's think about this illustrative educational example where I have this kid, Amin, and Amin's teacher wrote down like a bunch of things that she knows about Amin prior to me having interacted with Amin. Right, so here it says, Amin generally solves single-digit division problems fluently and uses repeated subtraction when working with large numbers. When asked to explain his reasoning, he often relies on what feels right rather than written strategies. And on it goes, right? Now, given this prior information, if I want to quantify my uncertainty on how good Amin is at math, right, I gotta first think about, okay, what does a latent parameter mean here? What does it mean to be good at math? How do I define that? And then I gotta define a probability distribution over this. This is what we call a prior. And given a particular realization of Amin's math proficiency, I gotta then define a likelihood, which defines the data that I'm gonna observe, which is basically the words that come out of Amin's mouth. So you can kind of easily see that specifying the prior and likelihood here is actually very hard for me, right, who knows nothing about math education. Right? And I'm not saying that this is impossible. I'm sure there's a lot of people who can do this, right? But to an ignorant ML person, this is basically me trying to specify a unicorn. And I gotta basically go and study math education for a decade in order to come up with a grounded perspective and argue that my unicorn is better than yours. Okay? So instead of this, in some sense, a very human-driven approach to coming up with probabilistic inference models, today I'm gonna pose a shift in perspective, where instead of thinking about uncertainty as arising out of latent parameters, which is obviously the standard view in statistics, whether you're a frequentist or Bayesian, right? I'm gonna now view uncertainty as coming out of data that is yet to be observed, okay? So my uncertainty on Amin just comes from the fact that I have not yet had the chance to ask him an infinitude of different math questions, right? But had I given this opportunity, I'm gonna know everything about him, right? So now I've circumvented even trying to define what math proficiency means, okay? And this perspective is actually very nice in that it seamlessly extends to what we call posterior inference settings, right? So let's say that now I've had the chance to interact with Amin twice, okay? I asked him, a juice bottle has 3.9 liters. If I share it equally among our teen friends, right, how many liters is each person gonna drink? And this is his answer. Now, if I assume that I have access to a large problem bank of math questions, right? Again, my posterior uncertainty on Amin's math proficiency entirely stems from the fact that I have not yet observed Amin's potential answers. So if I get an LLM to just simulate, autoregressively simulate out Amin's answers, right? I have now done quote unquote posterior inference under this view of uncertainty, right? Where uncertainty comes from missing data rather than latent parameters. And of course, an LLM is a probabilistic inference machine. So if I click on inference again, I'm gonna see a different trajectory. So in a nutshell, right, what I'm saying here is that under this perspective, you're gonna have a long trajectory of simulated answers from Amin, right? And the variability in the diagnosis that I can make out of these fake data is what reflects my current epistemic uncertainty on how good Amin is at math right now, having interacted with him twice. So it's a fairly simple concept, almost tautological, right? Almost obvious in hindsight. And to state the obvious, right? If I think about the red answers as the actual answers that Amin spat out of his mouth, and the blue answers as the thing that I asked ChatGPT to simulate autoregressively, right? Then this fact says that any statistic f that I can calculate off of this fake data tau hat, right? Its distribution is similar to that of the true distribution calculated on these potential outcomes that I actually saw coming out of Amin's mouth, right? Up to what we call the sequence prediction loss, which is what I have up there, It's basically just your log likelihood, right, that the ChatGPT, the LLM model, assigned on a means next answer. Okay? That quantity right there, it's called perplexity. This is literally the thing that the entire tech industry is right now trying to optimize by building nuclear plants. Right? This is the thing that we build scaling laws over. So what this fact says is that your ability to optimize sequence prediction, right, it governs also your ability to quantify uncertainty, your ability to do probabilistic inference. Okay? Let me say that again. A lot of the notation here doesn't matter at all. There's this term called perplexity that every LLM person tries to optimize, which is basically the next token prediction probability, right, the log likelihood. Okay, or the negative log likelihood, if you want to be precise, right? Now, this is something that we as a community are really good at optimizing the heck out of, okay? And what this fact says is that if you're able to do this on a means answers, sequence of answers, right, then you're good to go in terms of being able to quantify uncertainty on a means math capabilities, right? Okay. So in the interest of time, if I skip over to the empirical demonstration, here I'm going to take a actual data set from an educational platform called ED. Okay? And this is a platform that millions of students actually use. And I'm going to take a bunch of math questions, right? And these questions are actually pretty hard. 4 equilateral triangle tires are put together to make a new shape. Which shape is impossible to make? A regular hexagon, a parallelogram, an isosceles trapezium, and a regular triangle. I'm Korean, I have no idea what isosceles means. I've given this talk multiple times and I never really bothered to look up. So I actually have no idea what the answer here is. So the point is, these are pretty hard questions, right, for kids to solve. So I'm going to take a bunch of these questions. There's a range of different students who gave me answers to these different math questions. And then I'm going to take these answers to fine-tune a open weight model, Llama 3.1, right, to predict a means next answer over and over again. And there's hundreds of amines. Right? So was that? All right. A is the going once, going twice. Okay, so what kind of convinced me that there's something going on here, right, was this plot. It's known as the calibration plot for ML people, where on the x-axis, this is the probability with which the LLM thinks that it's right. And then on the y-axis, this is the fraction at which it is actually right. So ideally, if you want an LLM that is somewhat cognizant of what it doesn't know, right, a reasonable necessary condition might be that it be something close to the y equals to x line. Right? So this is very different from accuracy. And you can see that after having interacted with the mean once, right, the model is pretty well calibrated. And after having interacted with the mean 8 times, right, it's still pretty well calibrated without having done anything. So I view this as sort of a reasonable gut check, right? That tells me that, okay, this is doing something. Now, why do I actually care about fine-tuning such models? Well, as an OR person, I care about uncertainty to the extent that it actually impacts decision-making, right? Which is also what Ramesh was talking about at the end of his talk. So in this particular application, one way in which I can use this uncertainty quantification model is to build an adaptive exam, right? Amin is a 10-year-old kid. He doesn't want to interact with me infinitely, right, as I give him different math questions. So maybe I can build an adaptive math exam so that once I get one answer from him, I can somehow figure out what he doesn't know and then try to quiz him on these different concepts in order to get to reduce uncertainty on Amin's math proficiency as quickly as possible, which is obviously something that we're all familiar with when we're running adaptive experiments, right? And the way you can exactly formulate this as a concrete optimization problem as a Markov decision process is to think about your objective as the amount of uncertainty, the entropy that you have on these potential answers that Amin can give, okay? And then what are the actions? Well, it's the math questions that I can decide to ask Amin. What are the states? It's the current LLM, right, that has implicitly a posterior. Okay, so there's this thing called in-context learning, which is a long word for basically chugging more stuff to the prompt of your LLM, right? So as the LLM sees more information, it's going to implicitly sharpen its posterior on what it knows about a mean. Okay? So I want a nice decision-making algorithm that can select a math question that can maximally reduce my epistemic uncertainty on a mean's math capabilities. A mean's going to actually say something. Based on this, I'm going to calculate the reduction in entropy, okay, on his future answers. And I'm going to chug more of his actual answers into the prompt that I give to my LLM. Okay? And this is the quote-unquote the posterior update. So notice here that I didn't have to do any MCMC, right, or HMC or some other MC, right? I didn't have to check whether my Markov chain actually converged. All these really hairy things that you got to worry about in typical Bayesian inference, excuse me, you don't actually need in this framework, because in context learning, chugging more stuff to the prompt of your LLM, it just obviates that need. Right? And I'm going to show you two extremely simplistic decision-making strategies today, myopic policies, one-step look-aheads and two-step look-ahead policies. And here you can see that if you think about when adaptivity is going to help you the most, right? It's really when you're a weirdo, right? If you're a run-of-the-mill basic person, right, whose questions, math concepts that you struggle with are exactly the average concepts that everyone else struggles with, there's no reason to be adaptive, right? So the only instances in which adaptivity is really going to help you a lot is for the math questions, right, for which the students get wrong, but they're very atypical. So this is sort of how I've bucketed these questions. And you can see that as these questions become more atypical in this sense, these adaptive strategies, even when implemented with this very, very simplistic dynamic programming view of one-step look-aheads, they can actually improve materially over the baseline. And notice that if you think about this problem, right, where you're trying to do somehow adaptive experimentation in the space of questions, right, it's actually really hard to even start writing down a reasonable prior and then to think about how do I do Thompson sampling over the space. So that's what I really like about this framework, in that I can just put on my ML hat and optimize the heck out of some differentiable loss. Okay? Now, the main theoretical insight that I'm going to show you is basically, I mean, there's actually a bit of information here. It's not just a theorem statement for the sake of proving a theorem. And the main thing that you're worried about in these types of decision-making problems is that, look, your LLM, right, it's just a fake simulator. There's no way this is actually going to be an accurate representation of what a mean's going to answer, right, to your math questions. So then if you keep on making actions based on the LLM's, I guess, simulated predictions, then what if after a while, the thing you get to, right, looks nothing like the ground truth posterior state, right? So the action you take is actually not the optimal action that you should have taken based on the well-specified posterior, and these types of misspecifications can really mess you up. Okay, so I think Theodorus is in the room somewhere. Theodorus has a very interesting paper that basically says that in the worst case, right, these types of misspecified beliefs can really wreak havoc, right? Your regret can be very bad. And today, I'm going to show that this is definitely true in the worst case. But if you think about the average case scenario when you average over your prior, you actually don't have much to worry about. Okay? So this basically dispels this pessimism, again, in the average case. And for the theory-minded people in the room, MDPs are almost impossible to analyze, at least for me. So we're going to go back to a very simple multi-arm bandit setting. And instead of these, one-step look-ahead style policies, I'm going to look at Thompson sampling, which is a very simple principled algorithm, right? So for those of you who haven't seen Thompson sampling in a while, right, what is the Thompson sampling principle? The Thompson sampling principle implements the optimism under uncertainty by drawing a realization of a mean's math proficiency from the prior and then taking the action that is the best according to this drawn latent state. Now, what does Thompson sampling mean in this view of uncertainty as arising out of missing data? Well, if you think of these orange arms and blue arms, right, as my actions, and Z as the prior information, it just means that I'm going to use an LLM to simulate out fake outcomes, fake rewards I'm going to observe from these actions, right, after having observed 2 real outcomes from the orange arm and 1 real outcome from the blue arm. Okay? So these are my hats, y hats. So now that I've done a posterior draw, right, I'm going to calculate the actual underlying average reward for each arm by just taking the sample average. Okay? And then under the Thompson sampling principle, what do? You pick the best one. Very simple. Now, for those of you who've ever had to grapple with implementing Thompson sampling with text features representing context or arms, right, then you'd have had to think about all kinds of different hacky ways in which you can integrate deep learning into these types of exploration problems. And it's something that's very difficult to do. Under this view of uncertainty, there's a seamless way to do this, which is basically just to fine-tune a sequence model on the rich data set that you have at your platform, and then just do the simulation at test time. Okay. And what our main result says is that the fake Thompson sampling that we implement with my learned LLM, right, the regret that it achieves is comparable to the bestest thing that I cannot implement, right, that of the Oracle model that has access to the true posterior states, up to the perplexity loss, the sequence prediction loss. So what this says is that if you're a really good ML engineer who can build up scalable systems, right, to optimize this quantity, the validation loss, then you're also in really good shape in terms of your ability to perform adaptive experimentation. All right, so I have a couple more minutes left. So now, now that I've talked about, I guess, this, in some sense, a bit of a rigid view, right, of how we can capture uncertainty by employing these basic ML principles, now I'm gonna basically crap on this, right? Why is this still not bitter lesson pilled enough? Well, here I'm basically telling the LLM that, okay, here's a posterior inference, and I'm going to implement it by sequentially predicting out the next outcome. And then I'm going to take that, formulate some fancy MDP, and try to solve this using approximate dynamic programming methods or other heuristics like Thompson sampling. And this is all fine and good, and it can work in some of these Rexis-style settings, but I don't think it's good enough to actually get to self-improving agents. Because if I go back to that MBA example, right, MBAs they have no idea what a posterior is, right? A posterior is your backside, right, as far as they're concerned. And they do fine solving the MDP of life. They're very good at thinking about which things they don't know right now, and then acquiring these new skill sets over time. Right? And I think that instead of basically me cramming how to make discoveries into the LLM this way, right, perhaps a more scalable approach that we can pursue in the next decade or so is to get the LLMs to figure this out themselves. So this then leads to a view of agentic systems where you, instead of viewing LLMs as a reservoir of humanities discoveries, you start thinking about them as algorithms. An algorithm that maps stuff you've seen so far to stuff you want to do next time, right? And that's what we call an RL algorithm. And I think humans like me are very limited in their ability to write down good RL algorithms, right? So instead of me trying to write down some fancy RL algorithm that can actively explore in the space of code, which is very hard, right? Maybe we can meta-train such algorithms over a large body of curriculums. So this is sort of what's top of mind these days in the past few months. Okay. All right, so I'm almost out of time. This is the set of references that I talked about, and if you're interested in the meta-training pipelines that I ended on, come find me after the talk. I'd love to chat more. Thanks a lot for your attention.
Cool, that was great. Ramesh, maybe join us on stage, and we'll take some questions for both of our presenters. Yeah, I think that was really interesting, especially the connections around thinking about how uncertainty matters for decision making. And so somebody who's also been thinking a lot about that, what came to my mind is what set of problems downstream, what set of decision problems is some particular approach sufficient for? And I think, Ramesh, you talked a little bit about that in terms of, hey, are these problems about choices about treatments that have the sign consistent property? And I was thinking about some of the same things in your setting as well, Hong. So I wonder if either of you want to say about how can we expand the set of decision problems for which some of these kind of results that maybe quantifying uncertainty in this easy or fast and loose kind of way would be sufficient.
Either way. Yeah, I mean,
Yeah.
I guess I would actually just start by saying, I didn't say this in my talk because I knew a little bit about what you were going to say, but where my head is at is very much like an RL view of experimentation. And one thing in RL is, as I think you laid out clearly in your talk, you start by thinking about defining the decision problem first. So even, I think there's like, one question is like, sort of how does the nature of the downstream decision problem impact the kind of UQ you look for right now? But I actually think a more basic, like task zero, is defining the decision problem carefully. And I'm often struck by how this doesn't happen organically, even actually for the decision makers. A good example of this is the kinds of questions I'm especially interested in involve sort of decisions that don't get made very frequently, right? And that's where like Bayesian thinking, I think, is crucial. So think about launching a new business line, right? That's something where you usually just don't think of data scientists being in the loop in as fine-grained a way as we are with experimentation. I think part of the reason is the decision problem doesn't get defined very carefully in terms of like how data is contributing into that decision. So I think this is one thing in the RL community I think they're thoughtful about is thinking about defining the decision problem carefully. So I guess I'd love to hear your thoughts, honestly, from that perspective because of the kind of work you've been doing. But I think that's partly where my head has gone is, let's try to write down essentially the MDP the business is trying to solve in a more precise way.
A lot of what grounded me in thinking about the ideas that I presented today was in typical recommendation system contexts, you have a very quick embedding-based retrieval system where you basically come up with like 100 different items that can potentially recommend to you, and then you have a second pass ranker, right, that sorts these, and then you show, say, the top 5 items. And a lot of the so-called active exploration works that I've seen in the community are mostly at the level 2, right, where you basically come up with some ensemble model and try to explore a little bit. But in some sense, the meat, right, in ML is in the feature representation. And we need to learn embeddings that can somehow reflect how much you know about this particular item, right, and this particular person, and then continually try to sharpen your representation as you see more. Doing this is obviously very hard. And I think I'm excited by these ideas because it's a solid gradient step, a very incremental step towards that direction. But having said that, I guess ultimately what drives me as a researcher is the ability to build interactive systems. So I think one of the reasons that these agentic systems haven't had a lot of impact in daily workflows is because in most important workflows, the prompts that we give to these LLMs are underspecified. Your manager never sends you a 30-page instruction manual. They send you an email, look into this, right? And the prompts I give to Cursor, right, are somewhat similar. I try to be careful, but not that good. And then it just makes a bunch of random assumptions because it doesn't know what it doesn't know. And then it just rolls with it and generates a bunch of slop that I eventually have to revert to the previous commit, right? And if the LLMs are actually capable of trying to resolve these ambiguities in an interactive manner, then I think this is actually going to be quite transformative in terms of the impact that agentic systems can have in white-collar work.
Yeah, that's a good point.
Cool. I think that was great. We're going to take questions from the audience shortly, so I think there should be people with microphones around. I just one more question, and maybe this is related to the first one, and also some details in what you were presenting, Hong, was you said, hey, this is all going to come down to this perplexity, right? But a lot of that could really depend on that perplexity is sort of computed over this distribution of sequences, and that distribution of sequences has something to do with the distribution of sequences that are showing up in our decision problem. And so how do you think about that? I mean, in some ways, these companies spend a lot of time making sure that math problems and people's performance on math problems are somehow in that data set. But for some tasks, the perplexity that is being computed across some very large corpus
Totally out of distribution.
Is totally different from what we're trying to do.
Yeah, that's spot on. So what I guess for context, what Dean's pointing out is that basically the entire framework that I proposed today assumes that there is overlap, right, in the training data, and that you've actually seen all the possible math questions that you can throw out to different people, which may be sometimes a reasonable assumption in certain contexts, but in general, that's never true, right? So in some sense, I'm assuming that you've already randomized in your training data, which is the hardest problem, right?
Yeah.
So I've assumed away actually the meat of this. And I don't think there's a fundamentally an easy answer to this. This is why places like Anthropic are literally pouring billions to build post-training environments like matrix-like replicas of Salesforce so that they can train agentic systems, right, on these replicas. So what gives me hope is that if you think about meta reinforcement learning, meaning instead of me trying to be smart and clever and just decide what a good RL algorithm is, if I actually try to learn an effective RL algorithm, would that actually generalize across different problems? And I'm still, somewhat mixed in this dimension, but if you think about, say, Olympic level athletes, right? I think a lot of people in our society hold the view that because they're so principled and dedicated, they're able to do other things in life quite successfully once they retire, right? So in that sense, maybe there's some hope that these principles can generalize, but this is highly speculative.
Yeah, and I think just maybe this also connects with some of what you were talking about, Ramesh. Are there tools that we could use to find out when we're sort of in the good part of the space, right? When it turns out that the problem we're facing is one that's in either kind of as close to what we have in all this training data that we're computing perplexity on, or that we're facing a decision problem that's
it's
covered
really
by the
interesting.
theory.
I didn't talk about this at all in the talk, but another large project we've had over the last 5 years has been related to remote patient monitoring for diabetes. And the kind of thing we're working on is almost exactly this question right now, which is that let's say that you have some model that's building a UQ cone forward from where you're at right now. Let's say as a patient, you're forecasting glucose trajectories into the future. One of the actually important things you want to know about the model is whether it can even capture the nature of that trajectory into the future. Not, again, from the perspective of variance, but actually bias. Like, does your model fundamentally not have the ability to represent the sequence that will emerge in the future? And what's actually interesting, I was surprised that, it felt to me like the work that you were presenting also naturally admits the possibility for the model to be self-aware that it's operating in an OOD environment, provided that it's interacting with the world. I think if it's entirely offline, like this autoregressive sequence generation is entirely offline, clearly that's not possible. But as soon as you move to an agentic system, then you actually do have the opportunity to see whether or not the environment you're operating in puts you into a regime where you're actually OOD relative to what you've seen before. So that's the kind of idea we're exploring in this diabetes context right now. Yeah.
Cool. I think we've got a few questions from the audience. Yeah.
Yeah, it's such a question for both of you. But both of you had results that were like, you don't have to worry in this situation, whether it's your treatment sign aligned or you're not in the worst case. But do you have thoughts on like, how do I know that I'm in this situation where I don't have to worry versus I'm in the situation where I really do have to worry?
I have some thoughts on that, but I'm actually
I can start because I guess my answer is relatively simple in that if your val loss is good, you're happy, right? So that was sort of the whole point of this, in that I can just put on an ML hat and look at all the usual things I would validate my prediction models on, and assuming that this relatively restrictive assumption in your data generating process is true, then you can just trust the val loss.
I mean, I guess to push back on that a little bit though, and I don't know if this is where James was going, but like, I guess if if you're working on alignment, let's say, and you're worried about catastrophic risk, then isn't it true that sort of the rare event that you were, the rare event that sort of is actually the worst case is something that people really care about?
Good. So fundamentally, I don't think there's any silver bullets here, right? So I think all you can do is basically figure out how much diversity you can leverage in your current pre-training corpus.
Yeah.
And I think one thing that I've been proven wrong over and over again is the breadth and wealth of the information that's on the internet. So I think I would take this to the extent that if you believe that there's a bunch of stuff on the internet, good or bad, then maybe this can actually inform your decisions to a limited degree.
Got it. Yeah, and then, I mean, on the treatments front, James, kind of, I guess I think about it, that it's, maybe this is a non-technical answer, okay? But I sort of feel like I would default to not removing bias as long as the velocity of experimentation is high. And it's interesting because it feeds on itself, right? Like you're sort of like, maybe what I'm saying there, if the power is higher, the test ends faster, essentially. And so if there's smaller tests and they're ending faster, I think it's good to have this like 2 time scale view of experimentation. And there's other sort of moments at which you run larger tests where you invest the effort to actually think about debiasing. Now, sometimes, yeah, maybe you learn that in fact these treatments were changing your environment in ways you completely didn't realize, but that's back to the OOD type of question that we were just asking. I do think though that this is again a place where RL is very cognizant of this trade-off. There's sort of like a information velocity issue, right? Like, the longer you wait to get precise information, the slower your decision making is. And this is a thing that I think in experimentation, especially when you're focused on frequentist single test inference, you just tend to lose sight of that fact. And almost all the interesting work that happens when you start chaining experiments together. So Tim Sudajono gave a talk yesterday about experimentation programs. I think it's such an important perspective because that's the only time you start thinking about these opportunity costs between information and velocity. So that's kind of how I think about it right now, but it's, again, not a technical answer, it's more qualitative, yeah.
Do you think about that at all in terms of particular ways that firms might have a kind of hybrid experimentation strategy where people are running these kind of high velocity experiments that maybe are biased, but there's things like retrospective holdouts or something or reanalysis or meta-analysis of these experiments to assess the degree of bias?
Yeah, I think it's actually, I guess I think of it in terms of 3 different things. So one is to try to understand the performance of a naive approach, like I've been doing in this talk. A second one is alternative experimental designs, so clustering, switchback randomization, that you don't run quite as frequently, but you reserve for these kind of longer, sort of large-scale things. And I think the other one is actually structural modeling. So a good example would be like search ranking, for example, right? So search ranking testing can have all kinds of spillover effects, especially in these types of marketplaces. But I think one of the things that we're now actually able to think more creatively about thanks to LLMs is far more flexible choice modeling. And as soon as you're able to model choice in a flexible way and feel like the posterior over the choice distribution that you have, given past data, is actually sort of precise and well calibrated, you've actually, you can structurally remove a huge amount of the spillover effect in a test just based on what you collect in a naive experiment. So I think these kinds of ideas, at least when I started working on these problems, we tossed aside because we just were not operating in a world where the model choices available to us were flexible enough to structurally remove interference. But I actually think there's a lot of evidence that the flexibility, the kind of black box flexibility that a lot of these models provide us, LLMs, frontier models provide us, can be rich enough to actually start to remove some of that structural bias.
I think we have maybe another question over here, or right here. Cool.
A question to Ramesh. I didn't fully follow. Why is it that the markets are more competitive than the experiment? Can you reflect more on that?
Oh yeah, sorry. And that's, you mean the last thing I said about the overestimation. So the way to think about it is that in global treatment, I have a collection where the customers are more likely to book given any state of the market. In the experiment, some customers are more likely to book given any state of the market, but some are not. Now, from the perspective of a treatment customer, they see a more competitive world in global treatment because all the other customers are more likely to book, but only some are in the experiment. And as a result, if I think about global treatment as being the S-demand, that's the thing the first term in the difference in means estimator is trying to estimate, then I overestimate that in the experiment, basically because sort of in colloquial terms, the treatment customers in the experiment just see a world in which there's more stuff available to them than there is in the
And so do you need a finite number? For example, like if I have an infinite supply, would this still apply?
No, that's exactly right. So that goes back to kind of the first comment in the talk. If you remove the congestion effect, then bias is gone. And to first order, I mean, it's a funny thing, you know, when we wrote that first paper with Hannah and about congestion, honestly, I think that remains, in my view, probably the single most important thing I would tell someone about what to do about interference is to randomize on the short side of the market. It's like one sentence. It's very implementable. It doesn't require to change your experimentation stack. And I fundamentally believe it optimizes bias, you know, without changing your variance significantly. Yeah.
Yeah, I think that's a very practical recommendation, though. I mean, maybe to some people in the audience thinking, it does require changing my experimentation stack a little bit because all my metrics were computed
on the other side. Yeah.
So,
yeah. Fair enough.
Say,
fair enough.
It's easy, and then they'll spend a quarter trying to make sure that everything works for
Well,
them.
the good thing is that as an academic, I'm more than happy to collaborate if people feel like it's hard.
Cool. Maybe do we have one more question over here somewhere? Or over here? Okay. Yep.
I have a question about the calibration part of the second talk. So we know these models are overconfident most of the time. So we can either ask the model, hey, give me an answer, and also tell me how confident you are, or we can do more work and extract their log probabilities and do the calculation ourselves. In the applications I have tried, the calibration is usually like pretty ugly. So your ECD plots are the best I've seen. So are you just lucky, or have you done any post-calibration steps on top of the model's output?
No, so that was sort of the context here is that there's mounds upon mounds of work on to LLMs know what they don't know, and all kinds of different ways, just asking ChatGPT, how sure are you about your answer, ranging from that to looking into the token probabilities. And basically, it's sort of the wildest out there, right? There's results that say they know stuff, there's results that also say they don't know stuff, and in general, the fundamental problem in all of ML is that these models, right, they're omnipresent, they're always on, so then inevitably they encounter inputs that they didn't quite see during the training process, and they extrapolate, but they don't know when they're extrapolating, right? So we call this robustness, fairness. I guess the latest word for this is hallucinations. And how do you actually get models to be cognizant of these types of extrapolation behaviors is obviously a huge open problem. The short answer is I have no idea in general, but I guess I've mostly restricted my scientific findings to these simple math multiple choice questions. And on these, it does seem that fine-tuning does yield meaningful calibration behaviors. But speaking a little bit more freely and qualitatively, what I think I now believe in is that if you expand the pre-training data to be a lot more diverse than the end application you care about, then the incentives that the pre-training process introduces in terms of overfitting, right, being overconfident in your predictions, it's virtually dissipated, especially in the compute-constrained regimes that we often live in pre-training, where you have all of the tokens that humanity's ever generated, you steal them right off of the internet, and then if you pre-train on it, you can't really pre-train on everything possible. So then this is very different from the typical ImageNet era deep learning, where you loop over ImageNet multiple times. Right? So I think this is actually the key difference, whether you're in a data-constrained regime versus a compute-constrained regime. And if you're in the latter, then I think a lot of the training loops that you run actually reduces the overconfidence aspect of these models.
It like regularizes, basically.
Right.
Yeah.
Right.
Yeah, I was also, when I saw that calibration plot, thinking, okay, he's going to show us one next that's really miscalibrated, right?
Sorry to
And that
disappoint.
didn't happen. So, cool. I think we have to conclude here because we're going to go into the break, and then in just 15 minutes, the next parallel session starts. So we'll have Bayesian inference up here, and then all you frequentists have to go downstairs. So let's thank our two speakers again.